Hello everyone. In today's video, we'll learn how to multiply matrices together. We already know how to multiply a certain matrix sized m by n with a vector whose entries is the same number as the columns of the matrix A. I recall that the definition is just a linear combination of the columns of A with coefficients, the entries of the vector V. The output of this has the same size as that of one of the columns of A, which is an m by 1 vector. It has as many rows, as many entries as the matrix A has rows. Now, let's think about the following question. Suppose I have another matrix B of size p times m. Then I can definitely apply B to the vector A times V that I just got, this vector here. How can we understand what happens when I multiply B by the vector A times V? We should think about multiplying by a matrix as some sort of transformation in our space, meaning that we started with a vector V right here in a space Rn, and then when we multiplied by the matrix m by n, the matrix A, we got a vector A times V, which lived in Rm. Now we're wondering, okay, what if I take another matrix B of size p times m that takes a vector in Rm and spits out another vector in Rp? Is there any way that I can do this procedure of multiplying by A, then multiplying by B more directly with just some other matrix C of size p times n that directly sends V to C times V? In other words, does there exist a matrix C such that B times AV is equal to C times V? The answer is yes, and let's have a look at how that matrix should look like. By doing some computation, we can see that B times AV looks as follows. AV, as we said above, is, maybe I will rewrite it, is what I get by taking columns of A and multiplying them by the entries of the vector V, all the way to a n times Vn. When I multiply B to this, well, the multiplication between matrix and vectors is distributive, so I can write this as B times A1 V1 plus B times A2 V2, and so on until the end. B times AN Vn. The next step that I should do is to remember that multiplying a matrix by a vector times a scalar is the same as factoring out the scalar. So I will do that. This first summand is the same as writing V times B times A1 plus V2 times B A2, and so on. The last term is Vn times BAn. Well, but now I have written this as a linear combination of the vectors BA1, BA2, all the way up to BAn, with coefficients, the entries of V, V1, V2, Vn. This is exactly the same as writing V, the vector V, times a matrix whose columns are the vectors B times A1, B times A2, B times A3, all the way up to B times AN. Therefore, if we want to write B times AV as a matrix times V, then our matrix C that we're looking for, and we define it to be the matrix B times A, must be defined like this. It must have columns BA1 through BAN. That is our definition. Let's make it more precise here. If I have two matrices, B, which is size P times M, P by M, and A, which is M by N, then their product, B times A, is the matrix whose columns are the vectors I obtain by multiplying the matrix B by a column of A. Notice that for this definition to make sense, we need some dimensions to match up. In particular, we need the columns of A to have the right size to be able to multiply them by B. A way that I remember this is that if I put the sizes of the matrices next to one another, like I did here, we need these two sizes to match. And once we do that, then the outcome of our product will be given by the leftover sizes. Here it is. So that is another way of saying that B times A will be a matrix of size P times N. And it's only defined when the number of columns of B is the same as the number of rows of A. Let's have a look at an example. Here, there are two matrices. Let's just do a quick check before we compute B times A about the fact that B times A is indeed defined. B is size 2 by 3, and A has 3 rows and 4 columns. So we're in luck. We can multiply them with one another because the number of columns of B matches the number of rows of A. So the outcome that we would expect will be a 2 by 4. Let's do the computation. So B times A is the matrix defined like so. BA1, BA2, BA3, BA4. Let's compute all this. BA1 is given by, I have to take a linear combination of the columns of B given by weights in the first column of A. So this is 1/4 plus 2, 3 plus 3, 1. And when I add them all together, I get 6 and 8. BA2 is equal to a linear combination with the weights given by the second column of A. So I'll have 1, 4 plus 0 times the second column, 2, 3, plus 3, 1. When I add these together, I get 1 plus 3 is 4, and 4 plus 1 is 5. Maybe I will write the other two down here. When I take BA3, then that's 1, 4 plus 2, 3, which is equal to 3, 7. And BA4 is just the first column of B. That's 1, 4. So let's trace back what we did and write down our matrix B times A. This matrix will have as first column 6, 8, then 4, 5, 3, 7, 1, 4. And in fact, you see that the size of this matrix is, as expected, a 2 by 4. Here's the 2, and here's the 4. A word of caution is in order. Matrix multiplication, unlike number multiplication, is not commutative. In other words, it is not true that A times B is equal to B times A in general. Something could get very wrong. For example, here's the example we just did. We have a 2 by 3 and a 3 by 4. If we were to try to compute AB, then we would be multiplying a 3 by 4 by a 2 by 3. This cannot be multiplied because these two numbers don't match. So AB does not even exist in this case. However, even if both AB and BA exist, they need not be the same. here's a little example. Suppose that A and B are these two matrices. Then let's compute AB. To do that, I need to take A times B1 and A times B2. Let's just do it here. If I multiply A by B1, I get 1, 0. And if I multiply A by B2, I get 0, 0. When I multiply B times A in the other order, this would be B times A1 and B times A2. When I multiply those, B multiplied by A1 is a pair of zeros, and B multiplied by A2 is 0, 1. Those two are very different. They're not the same matrix. So beware, the order in which you multiply matrices is important. Let's have a look at another example that will help you make sense of the fact that it makes sense, it's expected that the order changes the matrix. So here's a couple matrices, a 3x3 matrices A and B, and we'll try to multiply them to the vector E1. We should think of this as matrices that transform vectors. So they eat up E1 and spit out another vector. If I were to compute AB times E1, that's the same as computing B times E1. B times E1 is the first column of B. So this is A times the first column of B is 0, 1, 0. That's what E1 does. It extracts the first column of A. But this is the second column of A, because this is E2. This is A2, which is, well, accidentally, it's another copy of E2. Let's compute the other order of the matrices. B times A times E1. This is B times A E1. Well, A E1 is a copy of E3. So this is B times E3. Well, let me write it like this. A times E1 is A1, but B times A1 is the same as B times 0, 0, 1, which is the third column of B, which in this example is E3. So what have we done here? Here's our upshot. We started from a vector E1, and then we multiplied it in the first one of the two computations, we multiplied it by B. And when we did that, we got the vector E2. And then we multiplied E2 by A, and A times E2 is equal to E2. When instead we start from E1, we multiply by A and then by B, we get E3, which is different from E2. So if you think of matrices as some operations that transform vectors, it only makes sense that the order in which you apply the matrices matters, because the way they transform vectors is different depending on the order. If you're not familiar with order of operation mattering, think about that and in a very familiar thing that you do every day. You would never dream of putting your shoes on before putting on your socks. If you change the order of the operation, put socks on and put shoes on, something goes wrong. It's the same here. Multiplying by matrices has to be done in the correct order. If you switch the order, you get a different result. This is the end of the video. The conclusion for this video is that matrix multiplication, as we saw it, can be a little time-consuming. Let's go back to this example here. When we computed the multiplication between two matrices, we had to compute 4 vector products. In the next video, we'll see a faster way to do that. I'll see you in the next video.